So if I recall correctly, we want to talk about the tiering. We want Uma to focus on tiering first. Are there any other topics you'd like Uma to focus on for the Chalk Talk?
You know, for HA, there's a certain problem.
Uma, you are on the screen here.
Yeah.
With write activity and how it's maintained across nodes.
Slides, the Chalk Talk.
Okay. So I'm sorry. So Uma, we're setting the agenda. So we want to talk about tiering, right?
Sure.
And I'm sorry, sir.
Yeah. So in the case of an HA storage system, you need to have some sort of write activity be replicated across nodes and stuff like that. How is that done? Are you caching writes? You know, those sorts of questions.
Okay. So basically,
sure.
Uma, did you hear that? Did you hear the question? How do we sync?
Yeah, we will talk about the geographical site replication in order to achieve the HA across geographies, if I get the question right.
I think it's more from an HA cluster perspective. How do you guarantee the data that's written to one node is actually available to other nodes when that node fails, for instance?
Yeah. Okay.
Especially if it's being cached.
Right. The write cache is also shared in the most common configuration. The ZIL disk, the ZFS ZIL disk, is also going to be sitting on the JBOD. So when the data written to the ZIL is always available to the other node, which is going to take over the pool, right? And if that disk also fails, it's already set up in Mirror, right? So there are various types that are possible. The most common configuration, the write cache, is shared.
Yeah. So does that answer your question?
Yeah, it does.
Yeah. So basically, you can share the cache memory. So if one head fails, the other one has access to the cache memory.
You're sharing the ZIL disk.
Yes.
Not the cache memory.
I'm sorry. The ZIL cache.
Okay.
Yeah. Yeah. Oh, okay. So Uma, now people want to. The other topic on the board is talk about tiering.
Mm-hmm.
How we can tier from one class of storage down to another.
Right. So as you were mentioning, when you create a pool, we can create multiple groups of tiers. So each group will have homogeneous set of disks, right? For example, one group can have the data group, can have either NLSAS or SSD. And then to increase the performance based on the data type, you can create a more or less cache into the same pool. That's where you bring in the SSD tier into the pool, right? If a pool is hybrid, it really means that there is one set of data that is sitting over NLSAS or SAS or SSD. There's another set of data, which is most actively used data, which will be in the SSD tier. Right, so we use the regular ZIL and L2 org concepts in an improvised way to manage the most active data to be in the SSD tier, right? So that's what is auto tiering with respect to ZFS really means, right? And if performance is needed beyond what a physical disk tiering is offering, you really need to move that TSM to a different set of pool, which may be offering higher performance, right? So that's when the TSM migration really comes into the picture, right? So when you migrate, when you schedule a TSM for migration, for moving it to a better tier or a lower tier, we start the incremental block replication from one tier to other tier, and then the incremental replication starts. And initially, depending on the size of the data that is there in the tier, It can take a few minutes to few hours. Sometimes if it has got tons of terabytes of data, it can even take a large amount of data, including up to days as well, right? So it's usually it needs to be designed in a way that if volume needs a reasonably very high performance, then you need to put them on SSD to begin with, right? If there is an incremental need, you can manage it with adding more SSDs in terms of a read or write cache. And amount of read and write cache can be dynamically provisioned or automatically provisioned by our software, right? So you don't need to continuously manually tweak how much cache do I need to give, if I need to give boost the performance by X percentage, right? All that logic is built into the software. Only when there is leaps are needed with respect to performance, you need to move them across the tiers using the migration feature. Does that cover the question that was asked, or I can take some specific questions?
About the physical nodes, do they need to be identical in order to be grouped into a cluster?
Right.
Uma, did you hear that?
That's right. Right. You need to have physically identical nodes in a HA group. Basically, because a node really decides what sort of capabilities that it can offer in terms of the network speeds and the FC cards and network cards, etc., including the memory as well, right? So you need to have identical configuration among the nodes, at least in terms of RAM and network cards.
What if you're doing some sort of HA from node to node? Can those be different?
Sorry, was the question? Is the question what happens if the node is really different?
What happens if you're trying to do some sort of HA or migration from one node to another? Does do the nodes in each HA cluster have to be the same?
No. Migration is totally different. You're migrating the data from one HA group to other HA group. At that time, you need not have the nodes similar across HA groups, right? When the data is moved, it really goes and fits into the new HA group. And only among the HA group, the nodes need to be identical, right? So you can have completely different RAM characteristics, you can have completely different network cards, and then once the data is migrated, it gets reconfigured to the new HA group characteristics.
As we're speaking about caching and tiering on your workloads, if you do a migration, does it keep that into account, or do you just start from scratch?
Can you repeat that question, please?
Because we're speaking about caching and tiering here, a workload sits on multiple levels. Does that keep that into account when you migrate to a different location?
Does it attempt to maintain the same performance at the different location, even though it might have different constituent parts?
Yeah, but the workload has its history, right?
Right.
Good
the
question.
performance in cache, for instance, the cache warm started at the next location, that sort of thing.
Right. So the entire in the chart talk slides, I'm going to talk about the heuristics-based approach that we have taken. When a volume is moved from HA group 1 to HA group 2 or from pool A to pool B, we're going to carry forward not just the data, but the history of the workload pattern and the amount of cache that it is historically assigned to it. All the intelligence also is carried towards the new destination. And then we'll be continuously using that data to arrive at the resources that are required to guarantee the new IO ops, right? So I'm just going to talk about the deeper details in a bit in the upcoming slides.
Yeah. So can we go to the first slide in the deck? Yeah, that one, storage, that one, right there. Or, yeah, 2 down.
You can actually
Oh, the next one.
pull up the first slide. Yep.
Okay. How about that one? Yeah.
This?
Yeah, that one.
Okay. Is it good enough? I don't know.
Is that good enough?
Is it visible or?
Yeah, for me, I can manage with my local slides as well. I can see the slide on the screen.
I have an eye breaker.
As long as it's good for the audience in the room, I'm okay. You can actually maximize the entire screen, right?
Yeah.
You don't need to.
Uh-huh. I don't know how you move it. That's okay.
How's that?
Okay. Yeah, Oma.
Okay. All right. So unfortunately, we are doing a Skype talk. Sorry about that. But let me try to make it, as clear as possible over Skype. So first thing we wanted to talk really before we get into how we do certain things, the architecture-wise, what we really wanted to do was what VMware did with respect to providing a VM on a hypervisor, right? So as Greg mentioned in the beginning, in order to reduce the cost at a storage per TB per GB level, you definitely need to share a given storage array among multiple applications. That's a given, right? In an ideal world, you would need to have one dedicated storage array for one application, right? If cloud service providers are going to give a dedicated storage for every application, then economics are going to fall really apart, right? So if what we have on this slide is on the left-hand side, we have a traditional monolithic storage controller trying to give a storage for multiple applications as is, right? And versus on the right side, we have what we call a multi-tenant storage controller that's aware of the need for differentiating performances within the storage controller for various applications, right? So if you look at the left side, right, a storage controller really consists of an access layer, right, which can be either SAN or NAS protocols, NFS or CIFS in terms of NAS, or block level protocols or SAN protocols, FCI or iSCSI, right? So these access layer storage protocols are offered on top of some file systems or thin file systems or SAN file systems, etc., etc. But it really comes down to, how my data is going to be given certain storage controller resources, right? In terms of how much memory is given, in terms of how much CPU cycles are given, how many CPU cycles are given, and how many file system resources are given to my particular data path when it goes through either NFS or iSCSI, CIFS or FC, right? So ultimately, what really matters is, the storage controllers resources that are given to a given data path really decides the performance outcome for that data path, right? So in a multi-tenant storage controller, you need to have a very strict control on the storage controller resources given to a given data path, right? So at CloudByte, I think we have taken the approach of, coming up with a shell kind of a thing, right? Or a jail kind of a thing, where within that jail, you have the entire protocol stacks embedded, and also you have the notion of a complete control of storage resources within the TSM, right? So if you look at the anatomy of a TSM, it's equivalent to almost a monolithic controller, right? So it's a virtual storage controller sitting on a physical storage controller, and that's why we sometimes say that we actually are a storage hypervisor, right? A storage hypervisor emulates a physical controller to the upper layers in terms of calling it as TSM, right? A TSM will have the entire protocol stack, NFS, iSCSI, SIPs, and FC. And also in terms of networking, also we expose a VLAN and as many number of virtual IP addresses needed. Also, at the bottom, we emulate a file system within a TSM, right? There is a notion of complete control of storage control resources. And on the left side, you can see in the green box, there is a QoS controller that is inside a TSM, which will continuously be calculating how many resources that I would need in order to give the right number of IO ops to all the data paths that are going through the TSM, right? And this QoS controller is not just hidden inside a given TSM. There will be a global QoS controller functionality that will be continuously validating the resource measurements across the TSMs in a given node, right? So it's really a complex function of how we intelligently measure the required number of storage controller resources and give the storage controller resources accordingly to each TSM in order to give the required amount of the performance that is configured at a TSM level, right? So that's at a high level, how we are trying to give the selectable performance or guaranteed performance for a given volume or an application that's part of the TSM. Any questions?
I'll take that as a no.
Okay.
Okay, can we go to the next slide, please? Yep. So this is really the crux of our CloudByte IP, right? So as I mentioned, all that a system administrator or a storage administrator needs to do is set some policies at a QoS policies at a TSM level, right? So before you set the policies at a TSM level, you need to design your storage infrastructure in such a way that what's my physical infrastructure? I will design multiple tiers, right, in terms of creating pools. And I will give these pools ownership to individual nodes inside HA groups. And once my physical infrastructure is done, I will start creating the virtual infrastructure, right? So the virtual infrastructure creation starts with creation of TSM. And once TSMs are done, these TSMs can be assigned to individual tenant applications, right? So at the TSM level, only what TSM.
You are breaking, Uma. Are you there? Oh, looks like there's a break.
Technology. Right till the very end, it almost made it.
You are able to hear us?
Yeah, I can hear.
Okay. Move on.
All right. So basically, once you set the QoS policies at a TSM level, in terms of either IO ops or throughput, you will leave everything else to the QoS controller on the node, right? So what the QoS controller does at a high level, it does two things, right? It converts the policies into the translations, right? For each QoS policy, how much of CPU, memory, and file system resources and disk subsystem resources that are needed. And these resources can be dynamically varying, right? Depending on workload patterns. For example, 60-40 read-write, can really depict a different threshold compared to 100% write on the disks, right? So sometimes you will need to give more disk bandwidth for different types of workloads. So we consider all those things into the equation. Translate those requirements for each of the data path. So that's really the resource translation part. And once the resource is translated, you should be in a position to really enforce those required resources into the system, right? If you look at the traditional file system, you will not be able to know who this data belongs to below a certain level, right? So once the NFS data is given to a file system underneath or the disk subsystem, you will not know who this data belongs to, right? So there are a lot of complex logic within the file system that says just about the disk firmware, right? Which will be contending for either reads for writes, etc., etc. So these reads and writes can be really belonging to various application or various tenants. So what we did to begin with is we really changed the ZFS architecture inside to make it aware of who the data belongs at almost every level till just above the disk firmware level, right? So right from the packet entering into the controller to the point that it goes to the disk, we are aware of who that packet belongs to, right? So when the packet is entering into a common queue, we have isolated those queue into multiple queues and identified or tagged them belonging to a particular identity or particular volume, right? So that's really called as resource tagging. And the resources, we have about 40 types of resources that we have put into our IP. And currently we have tagged around 7 or 8 resources in the current product. And with by controlling those 7 or 8 resources itself, we are able to get more than 95% of control on the IOPS, right? On guaranteeing those IOPS, right? So what we do once the resources are translated and resources are tagged, we follow the heuristics approach, right? We start with certain assumption, and then these are the amount of resources that are needed based on our experience, and then we start with that, and every minute the resources will be readjusted based on the workload characteristics and the resources available, right? So this is a continuous process, and then these heuristics are actually uploaded into the Elastic Center so that when a particular volume is moved across nodes, when a HA is failover happens, or when a volume is moved across the HA groups for migration, we continue to keep this heuristics knowledge of a given application at an Elastic Center database level, and then we continue to get a good IOPS approximation when the data is moved from one place to another, right? So that's really how, at a bit deeper level, how the IOPS guarantee or the performance guarantee happens within the file system.
Great. So are there any questions?
I get that from a high availability perspective, but can you acknowledge it again for storage fee motion?
So
because then we are manually moving it instead of the machine is moving it from a high availability perspective. Do you keep that knowledge when where the administrator does a storage fee motion to a different pool?
Yeah, so I think Uma covered it earlier that when the tenant storage machine is moved, all the history and logic moves with it.
There's two types of storage vMotions we're talking about here. One is at the VM level, VMware vCenter kind of level, and the other one is at Elasticenter level, I'm assuming. Yeah. And you're talking about the Elasticenter level.
Yes, we're talking about the tenant storage machine. Not when it moves, it carries its history with it, essentially.